So if you are ready, so we move on to, so we have studied the Maxwell equations. And remember, if you remember, we split them in two sets by studying the static limit. And actually that gave rise to electrostatics, that is a rather important subject, mainly because it's a very apparent force. I mean, we do have electrostatic forces around. If you have free charges, then the leading effect is this big Coulomb field, right? That's the reason why in the textbooks this electrostatics chapter or chapters are much longer than the corresponding one for the magnetostatics. I mean, magnetostatics is sort of, I mean, people knew about these weird materials, right, from magnesia in Greece, but not magnesia, the name comes from the name of this town, that attracted metallic particles, right? And then if you stroke some of these amber materials, then it becomes, that's probably from electrostatics, so yes. But there is no everyday manifestation of this except for these ferromagnetic materials, right? And therefore, as we move to the next set of Maxwell equation for magnetostatics, I think we can do it rather quickly and move on to the full set of Maxwell equations. But just there are a few things that one can do here. And so let me remind you that we have this set in which we study the curl of B. This is the curl of B, comes from some electric current that you have around. So if you have a density of charge or density of current J, this produces some curl of the B field. That means if you go around doing your line integral around some current, then you find out that there is a field, there is a magnetic field. I mean, and so like charges generate electrostatic fields, currents. You understand? These are steady currents. I mean, this is a current that is there, and it remains at that value. I mean, it's not a varying electric current. So if you have this current, like in a wire, like the one producing this light, then if you go around in your with your integral, you discover that there is a B field, a non-vanishing B field. So steady electric currents produce magnetic fields. And then it's always true, this is true also if you have varying fields, that there are no magnetic monopoles, and therefore if you do a surface integral, you find that the integration, there is no net flux of B fields out of the closed surface, right? So this is very different, is the main difference with respect to electrostatics, where here you have the divergence of E is proportional to how much charges you have inside your volume, okay? But the P field is not generated by anything, really, and therefore if you take a volume integral like this, right, and then you take the surface, the flux of B field, as much as comes in, it comes out, and so you have a vanishing divergence, okay? So this, in a way, we already know. It's always true also, so it's nice, and we can forget for the moment. And really, the study of magnetostatics comes from studying this function in some details. This thing has a name. It's called Ampere law, and gives the magnetic field generated by an electric current. Okay, In a way, I prefer the integral form, as I said. I mean, if I take, I use Gauss theorem and Stokes theorems, and then I have the circuitation of B, right, around some line. This is C. I go around, I integrate B, I integrate the component of B along this circuit. This is some integral of this density, and of course, if I integrate this density, I get the current. So you see, I get 1 over epsilon naught C square, the electric current going through this loop. Okay, so that's the physical meaning. And remember that this constant is what we call mu naught, right? So I think properly this is the Ampere's law. So it's the integral form of the Maxwell equation. So if I have some electric current going somewhere and I take a circuitation of B around that, I get that the Ampere's law is satisfied. Okay, that's all there is. So the magnetic field induced by a steady current is, you can compute it this way. In fact, we can immediately apply this very simple equation, and for instance, what is the magnetic field around a straight wire, right? That's the zero order problem. You have a wire carrying, I don't know, I call it, I, some current, okay, as probably there is behind this blackboard to turn this light on. So you have a wire, some constant current, I call it I. What is the field B in certain point here at the certain distance, let's call it R from this wire, okay? So that's the simplest problem. It's like is the equivalent of the Coulomb, what is the electric field generated by a single charge. Here you don't have a magnetic field generated by a single charge. You need charges moving with constant speed generating a current. So the elementary things that produces a magnetic field is the electric current. So I take electric current, I call it I, the intensity of this, and then I compute the field here. Well, this is very simple because you see I can just use Ampere's law, right? So I can say go around at the distance R. I take my circuitation, this C path, to be a circle of radius R around this current, okay? So for instance, I go this way. Then this quantity here, the left-hand side of Ampere's law, is what? Well, it's very simple because it's just whatever the B field here, the intensity of the B field there, right? So the B field tangential to this line times the length of this circumference that, of course, being a circumference of radius R, has to be 2 pi R, as you discover at the beginning of your geometry class. And because of the Ampere's law, this circuitation around, so this is C, must be mu naught, the electric current carried by this wire. So you see, I have so the intensity, the size of the B field. So the B field. So this is going to be like a force line for the B field, right? So there are like circumferences around this field. And because it's a force line, the B field is always tangential to this. So if you do that, and the intensity of this field, well, comes from here, right? It's just mu naught divided by 2 pi, 1 over R I. And so that's the simplest form of another law that you may find in the books, in the textbooks, that is called Biot-Savart. It's just one guy. It's not just, it's one guy with, one of those guys with the hyphen in the last name. They are very, he was a French guy. So. We will see, I mean, actually this is the experimental root of this Ampere's law. I mean, they sort of, well, okay, I'll show you in a second. Experiment, of course, how do you measure a B field? You measure through the force that is produced through Lorentz force by the presence of the B field. So this is the simplest expression, this Biot-Savart law, but experimentally it was really, they had wires, right, and they had current running through these wires, and they noticed that the wires were attracting one another or repelling one another, depending on the direction of the electric current. So that was sort of a random discovery. They were not expecting, I mean, the legend is that Ørsted, this was a Swedish guy, I think, or Norwegian, was just showing some other stuff, and then he noticed that in the apparatus the two wires were attracting each other, and so he started wondering what was what, and eventually they wrote this Biot-Savart law. So I'll come back to this in a second, because in fact I want to compute the force that you have between two circuits if you have electric currents running in the two. So that's the equivalent of the problem of what is the force between two charges, right? Because the elementary object, as the charge is for the electrostatics, the electric current is for the magnetostatics. So if I want to compute the equivalent of the Coulomb force between two charges, the equivalent is exactly this, the Ampere's law, the Biot-Savart law, that gives you the force between two electric circuits if you have electric currents running there. But before that, so this was a very simple example of the application of these Maxwell equations for computing the B field. So the other important example, so this is a simple and in fact important example. And of course the other important example is what is the magnetic field inside a solenoid. You know what a solenoid is? You take a, yeah, you take a wire, no? So you understand that if you have a magnetic field for each of those wires, you get some magnetic field like that. If you take a cylinder and you round up many turns of a wire, the interesting feature is that essentially you get a constant magnetic field inside. Then outside is sort of not constant. But inside you generate a perfect constant magnetic field. And what is the intensity of this magnetic field? Again, it's very easy to compute just by using Ampere's law, because let me take this solenoid, okay, and cut it across like this. So these little dots are the wires, right, that I've cut. So you have the wires going around, and I cut it orthogonally like this. You understand, right? So this is the wire that goes like this, and I cut it like that. And as I said, you expect inside the solenoid you have a constant magnetic field like that. So the only question is which you have to pick. You have to be clever and pick a wise path for your integral, and this would be something like this. You take it has to include some of the wires, because if there is no wires cut by the surface defined by this path, then you get 0, right? So you go around like this, and you include a certain number of wires. So this is going to be my C in this case. So let's say this is a length L. So you understand that by doing this, right, you get what? Here you have the magnetic field. Now take this very small, and outside of an infinitely long solenoid, you have 0 magnetic field. So this path, it has a non-vanishing contribution only from here. So you get this B, let's call it B naught, because it's constant. times the length of this path, right? And so this is the integral. And this is mu naught, or 1 over epsilon 0 c square, if I take this, the current crossing the surface defined by this. How much is the current? So I'm running a fixed current I, but through many spires. So I get I times the number of times the things go around, so something like this. So if I define little n to be big N divided by L, that is the number of turns the wires per unit of length, right, little n, then I can write B in a nice form, that is the constant B field inside the solenoid defined by this little n, so with the density of wiring per unit length given by little n is simply Ni divided by this epsilon 0 c square, or mu naught Ni. So that's a standard result, and is, as you can see, very easily derived by means of the Ampere's law, that is by means of this Maxwell equation for the magnetostatic case. Okay? So that's just to show you that if you give me your current, then if the geometry of the system is sufficiently simple, I can very easily, on the back of an envelope, derive the intensity of the magnetic field generated by that current. But of course, this Biot-Savart law, as I said, really comes from study the force that you have when you have a circuit with running currents in them. So let's do a little bit of that. So I want to study a little bit. So the Monsieur Biot-Savart law says, let me write it for a, this is sort of an integral form. So let me write the differential contribution. So a small, if I take a small section of the wire, okay, crossed by with a certain current running, I can write that so let me write it like this. Cube. So the Biot-Savart law, in general, this is for the special case of a single wire like this, in general is given by this, okay? Where this K depends on the, so let me now switch to Gauss units, so this is just 1 over C, if you remember. Okay? So if you take it like I did there, you recover the special case of that I computed before for a single wire at the distance r. In general, if you want, this was an empirical result, but now we derive it. As I said, there are two ways to do these things. Either you build up from results like this and you end up with the Maxwell equations, but I think it's easier the way we are doing it, that from the Maxwell equations you derive something like this. Anyway, let's just say that we have this result. So let's put it. So Gauss units. And what they noticed was that actually what they measure was that the force in a certain point R is this 1 over C, so I over C ds cross B at that point R. So that's what is called Ampere first law. Okay, so if you are at a certain point R here, the force here is given by the magnetic field, so the force on some small section of a wire carrying a current I is given by the cross product of this small, so you put here the small ds, times the magnetic field there. And the magnetic field is generated by some current somewhere else and is given by that. Now, is this a new result? I mean, from our point of view? No, it must be somehow, I mean, the force, we know that the force is what? The force is Lorentz force. That's the force that you get by putting something charged in an electric or magnetic field, a magnetic field in this case. So I must be able to rederive Lorentz force from this Ampere's first law that was derived experimentally, of course, before the Lorentz force. But that's the case because it's just a question of taking that this current here, right, that comes from a certain density of charge must be that for just a point charge, right? Let's do that. So if this is for a point charge, that means a point charge of charge q times the velocity, and then I put this very useful function that we already know, that is the Dirac. So this is the current for the current from a point charge. So for us, the fundamental concept is the electric charge, the point electric charge. Then the current is derived by saying that you have a current, in fact, you have a density of current if you have a charge moving in space, right, with a certain velocity. Of course, at the time, they didn't know about these charges, this stuff, so for them, this electric current, or the density, if you wish, to go on the local level was the fundamental concept. But for us, if I now put this in the definition of B, right? So I have my B field because of the Biot-Savart law at the point R is the integral of these things. Where here I don't have the macroscopic current, but I have some density of current. And for the density of current, I can pick the one for a point charge. So if I do that, you see that I get Q divided by C. These are just constants, right? Then I have to integrate this density. So I have V at the point R prime, where I'm doing the integral, times this R, that is R minus R prime divided by this cube, so R minus R prime cube. And then I get this delta function that is telling me where in space this charge is, this R naught. Okay, so just to, I have in R naught, I have my little charge with velocity v. And I'm looking what happened at the point R, where presumably I have a magnetic field generated by that. Okay? And I also have some force. I want to measure the force. And I have to do the volume integral on this R prime. But this is simple because I have this delta function. So the integral is killed by the delta function. You just replace everywhere the R prime with the R naught. So you get Q over C. Then the velocity at R naught, so the velocity where the charge is, and then this factor due to the distance between these 2 points, R and R naught, right? Yes, times nothing, because I've done. Yeah. actually, probably you recognize this Q times this is what? You have a charge Q here, and you are here. I mean, the charge is moving, so you have an electric current, so you have a B field. But you see, you also have an E field, right? And in fact, that is what? It's just a, yeah, it's just a Coulomb field. So actually, at this, I can write as 1 over C V cross E, where E is just the electric field generated by the charge. Actually, this is the first instance of this. You see, you have a nice relation between B and E for this charge moving. But at the same time, I can compute now the force for this B field, right? Again, the force is going to be, force in R is going to be 1 over C. Then you have to do this, so let me replace this IDS by the integral over a volume of the density of current, like I did here, cross the B field in R prime, and I have to integrate over the prime volume. And again, I put my choice, just the density of current due to this single lonely charge, okay? So I replace this by that, and you see that if I do that, I get here Q V cross delta, so not cross, times delta R prime minus R naught, right? And like before, the delta function allows me to do the integral right away, so I get Q over C V cross B. So the force is equal to this. And this you should be able to recognize right away is exactly the Lorentz force due to a magnetic field. Okay, so you see, they are not new results. Everything is included in the first blackboard that I wrote down with Maxwell equation plus Lorentz, but in this context, you can rewrite these terms. So at this, let me. So the last thing one can, the next level of generalization is, as I said, let's see what happens if I have two electric circuits, so two wires in which you have an electric current running, and what is the, so you have two loops like this with the let me call it so a I1, and here you have another one with a current I2. And what is the force between these two loops? So you have a current here and the current there, and so I want to use this Biot-Savart stuff, so I take a ds1 here, okay? So this is at distance r1, and I get a ds2 here at the distance r2. So the relative distance, the relative distance between these two, I can call it r1 minus r2. And the point is that this one will see some B field B1, right? And this one some B field B2 generated, or dB1. So this one is the B field generated by this wire. This one is the B field generated by the other one, okay? And because of this B field, they will attract or repulse each other with the force that I'm going to compute. So let's compute it here. Clearly, the force of this on that is exactly equal because of Newton's third law. So let me just compute that. So to compute the force there, first I compute dB2, right? So first I compute the magnetic field, the infinitesimal magnetic field generated by this infinitesimal section of the wire, and then I apply the force law that I wrote here, before, and then I erase it, and I get the force. So let's do that. So what is the B field? Well, this we already computed. It's just I2 divided by C in Gauss unit, then ds2 cross the distance that in this case is R2, R1 minus R2 divided by the cube. And therefore the force that I call F12, that is the force between these two loops, it should be just I1 now, because it's the current running there, divided by C, and ds1 cross the field there due to the, that is the one I just computed here, okay? So it's just, you see, before I just had one wire, now I have two wires. But so that's really the equivalent of the Coulomb force, right? I have two wires with some currents, and what is the force between these two? Well, so it's just a matter of plugging in, right? So you see, it goes like the product of the currents. So it's like divided by C squared. So in a way, this C square, no, C is a big number, you know, it's like 3 times 10 to the 10th centimeter, no, per second. So that in a way explains why, I mean, this is not, I mean, why the Coulomb force is rather strong force. This one is much weaker, right? This is carried by this coefficient. I mean, if you have two wires, it's not that they are, you know, switch on the current and they attract like crazy. They have this force, but it's not such a big deal. So that's why it was discovered much later. Why, if you have some charged things, you know, you have two charged spheres, they attract very strongly. You remember I mentioned to you that if the Earth and the Moon had just an excess of charge, I don't know, 10 to the minus something, they would attract much stronger than they do through the gravitational force, right? It's only the fact that all bodies are essentially with zero net charge is the only reason why we see the gravitational force, right? Because otherwise we only see Coulomb force because it's much stronger. So this one is stronger than gravitational force, but much weaker than the electrostatic force. So it's a sort of intermediate stuff. So you see it, but to see it, you have to make an effort. So I'm plugging in this in there, so I get this term, and then this cube downstairs. So to make a long story short, I get that this force is proportional to this factor. Then I have to integrate along this loop to get the B field, and then the net force I have to integrate over the other loop. So I integrate over the loop 1, I integrate over the loop 2, this factor here, ds1 cross ds2 cross r1 minus r2. And everything is divided by r1 minus r2. So you go around loop 1, you go around loop 2, you integrate this factor 1 over r squared, and you get the net force. In fact, this could be written in a nicer form if you use one of those formulas that I gave you, but I know that you already know. That is, if you have this famous, you see, you have a triple vector product. Those, they pop up everywhere in this stuff, in this business. So, I mean, this is not very nice because it's a vector product of a vector product. It's nicer to take the scalar product pointing in the B direction, right, minus A dot B pointing in the C direction, okay? So if I do this, so I take this double product, I call A, B, C, I just, you see, I get the minus I1, I2 divided by c squared, this double integral, and then just the r minus, so just this factor here. ds1 dot ds2. So that's nice because you only have to take the scalar product of these two sections of the wire, take the scalar product, and then you simply integrate essentially the distance square, very similar to the Coulomb law, you see, it goes like 1 over r square along those paths, and then the product of the current, you get the force. Any objections? How did I get that last step? You see that right away, or I should explain? Because this gives two pieces, right? Right? So A, B, C. So that is sort of this piece here, because you see A, B, C. So A dot B is this term here. So it's this. And that's why it has a minus. So what happened to this other guy? It's 0, right? But why? Okay, so that's the homework. Just convince, I mean, it's trivial, but just convince yourself that I'm not just, you know, I could have, maybe I forgot, maybe there were two terms. Okay, so essentially in half an hour we have covered most of the magnetostatics chapter, that I'm very happy because, I mean, there is not much else. You can do, again, an infinite number of exercises by drawing clever circuits, so let me give you just one. Well, it's part of the exercise to, to derive the exercise. It's in the book. It's not a theory that I developed. So the exercise is this. So first, convince yourself that what I wrote there is correct. Then just apply again these very simple things to what is the simplest example of what we just computed. What is the force between, so what is the force between two infinitely long wires, right? So I take let's say one goes up and one goes down with value. So this is the current here is I1, the current there is I2. The distance between these two wires, let's call it D. Okay, so what is essentially what is the, in fact, because they are infinitely long, what is the force per unit of length between two parallel wires, conducting wires. Okay, clear? So that's the exercise. Also verify when is this force attractive and when is repulsive, depending on the, if the current is going in the same direction or in the opposite direction. Okay, so this was really Ørsted experiment. That's the place where they first discovered that currents were attracted or repulsed by some mysterious force that now we know to be essentially due to the magnetic field. Can I read? Okay, so what can we do now? Well, if you remember, in electrostatics, it was a big deal, the fact that we wrote the equations by using the scalar potential, right? At the end of the day, the entire discussion of electrostatics boiled down to discussing the Laplace or the Poisson equations, and that equation was based on scalar potential, not the electric field. So one may wonder, can I do something similar here? I mean, it was nice not to have to worry about this vector field that was the electric field and to worry only about the scalar quantity that I call the scalar potential. So maybe the same trick, can I have the same trick here? Well, clearly I cannot use, I mean, there the trick was based on the fact that the curl of the electric field vanished, right? But that clearly is not going to work here. So it looks like we are out of luck. But of course, our eye goes to the next line, and okay, the curl is not vanishing, but now we have the divergence vanishing. And as you well remember, if you have if it was an exercise, if you have a vanishing divergent field, that means that field itself can always be written as the curl of something else, right? Okay, so not exactly what we wished, but the next best things is that we can replace the B field by the curl of another field. So it doesn't look like a breakthrough, but I mean, it's the only thing we can do. So let's see where we go from here. So I can take this and replace it in the other equation, right? So I take the curl of A. And this is equal to mu naught J. Now again, this is a curl of a curl. So again, we are in this situation of A cross B cross C. So you see how useful that formula is. So, well, what happened? I use again that formula, and in this case, I get that the gradient of the divergence of A, right, the first term, minus, now here I have the divergence of the gradient, so this is the Laplacian of A, equal to mu naught J. So that's encouraging, in a way, because this part here looks very much like the Poisson equation. The only difference is that you don't end up with one Poisson equation. You end up with three Poisson equations, one for each component of this vector field. Okay, so the B field is more complicated. So instead of having one Poisson equation, you are going to have three Poisson equations, because you have to rebuild first this field A. By the way, this field A is called the vector potential. That in a way is not a great name, because potential should be a scalar quantity, but okay, it's a vector potential. You understand why, because if you know A, then you know B. So this part is good. Is a Poisson equation for this vector potential, really three, because it's a vector. But how about this? I mean, this we don't like it very much. But there is a things that is called gauge invariance of these equations that we are going to discuss in a little while. But so just take it for what it is. Then you can make a choice of gauge, it's called. And in particular, this choice is that I take this and I put it equal to 0. So I take that you see, this A field is not completely fixed, right? Because if I shift it by certain combination, then it's still true that the curve doesn't see this fact, and you get the same B field. Okay? Right. But it's really an important thing. So I don't want to discuss it now that we are doing another thing. We will stop and discuss this in full detail, because this gauge invariance is crucial. Okay? It's an invariance that you can shift your scalar potential and the vector potential by some functions, and still the Maxwell equations, that is the value of A and B, remains the same. You remember I mentioned this because people, so then they think that the E and B are physical, while A and phi, so the potential are not physical, because you can shuffle them by this gauge transformation. So they cannot be physical. But okay, we come back to that because actually also it has a very profound consequence in modern physics, because this fact that the Maxwell equations are gauge invariant, that is that you can do a gauge transformation, they don't change, is the basis of all unification of interactions at the quantum level. Okay, so it's very important, this gauge invariance. So I want to discuss it in some more detail later on, but now is a side issue. I mean, I know that I can change A by a certain transformation in such a way to satisfy the fact that A is a divergence-less field, okay? And if this is true, this is good because I get rid of this term. Indeed, I have that the vector potential satisfy this three Poisson equations. So this is true in the Coulomb gauge. So this particular choice of gauge is called Coulomb gauge, I guess, because in a way, you know, this is like the Coulomb law, you remember, because, and so this is called the Coulomb gauge because then your potential satisfy the same Poisson equation as the scalar potential. Okay, so we are making some progress here because this we already discussed, right? I mean, we already know that to solve that equation, I can use various techniques. In particular, I know that, okay, component by component, this is exactly like the Poisson equation for the scalar potential. So I already know the solution, right? The generic solution, forget about the boundary condition for the moment, is just the integral of this current in the volume divided by the usual factor R prime. Exactly like the potential was this integral over the charge density, right? Because here I had the charge density before. Now I have the current. So, but I mean, it's a very incremental increase in difficulty. It's just I have three components because A is a vector, but each of those components has a solution of exactly the same Poisson equation that I had previously in the electrostatic situation. Instead of having the charge density, I have the current density in that direction. Okay, so everything seems very. Of course, this is. I still have this sort of gauge invariance, so I can always add here the gradient of a scalar function. Okay, but by fixing the gauge, I fix that scalar function, and particularly with this gauge, this is the full solution of this equation. Okay. Because I fixed the gauge. This is the terminology. Okay? Is this clear? I mean, this equation, I can always add here the gradient of some scalar function, simply because then this is not. But if I have this, but if this has to satisfy this is the generic solution. But then it has also to satisfy this condition. That means that this scalar function, this term here, must satisfy the fact that this is equal to 0, right? Because to satisfy that, I take the divergence of the gradient, so I get back the Laplace equation. Now, this has to be true everywhere, and so the Laplace equation has only the constant solution equals 0. That is probably what you had in mind before I introduced these boundary conditions. So indeed, in the Coulomb gauge, this is the generic solution of the Poisson equation. It's 0, really, because I take it to be 0 at the border. So it's 0 at the border, is a constant, has to be 0 everywhere. What is? The sign. The sa is? Yeah. Because you see, the boundary here means infinitely away. So I don't want anything there. That's the usual assumption that the universe factorizes. Did you go to this Arcania Med lectures? The last lecture he mentioned this thing that you always assume that if you are doing something here, it is not changed by something that you are doing very far away. This is the same thing. If you take your border, your boundaries are infinitely away, there everything must go to 0, right?
Does it have a physical meaning? Sorry.
Yeah. What? The scalar?
Yeah. We have a gradient of a scalar function, right? Yeah.
Yeah.
So the scalar function psi to 0. Does it have a meaning just psi by itself?
No, yeah, I mean, it can be, no, but then I want that to satisfy the Coulomb gauge. Then it must satisfy the Laplace equation.
That's true, yeah.
So to satisfy the Laplace equation and to vanish at the very far away, then these are surface terms that are always sort of put to 0. Remember, every time we do this integration by parts, right, we always have these border terms, the surface terms, and we always assume that everything is smooth and goes to 0 sufficiently fast that we don't have to worry about those. Otherwise, it's of course, well, that's not always true. So what is the vector potential for the previous problems that we compute? What is the B field for a loop? So back to the previous problem, we have our nice loop in which a current I runs, right? So if we take a small section of this loop and we go to a point P here, what is the magnetic field there? Well, we already solved this problem using the Biot-Savart law, but now we can solve it by using the general solution of the Poisson equation for the vector potential. Because you see that, so my vector potential, now I erase it, so I have to write it back. What is it? It was mu naught 4 pi j r prime d3 r prime r minus r prime, right? So now so this is true for any distribution of density of currents, but now I pick again a very special case. So what is there? J d 3r prime is what? Say J, so say this wire has a cross section S ds, right? So ds is this and S is the cross section. So that means this integral is J times the cross section times this ds. But J times the cross section is just nothing but the current, right, going through. Everything is uniform and constant. So if I multiply the density of current times the cross section, I get the total current going through that wire. So you see, it simplifies to just mu naught divided by 4 pi. Then I only have to integrate I ds. And then I have this distance here that I can just call r. So I have the integral over r. So this is the vector potential of this loop, this conductor loop. And then I can just use the fact that, so what is B? Well, I should get back my previous result. And if I take the curl of A, that is the curl of mu naught over 4 pi, the integral of I ds over R, I should get back what I had before, and that's what I get. So I can call R, so let's call R, well, I call it R. So let's call R ds2, so R12 if you want. If I call this 1 and this 2, R12 square. When you take this, that is what we had before. So, as you usually, this is the standard procedure. You find the vector potential, and then from the vector potential you get the B field. As for the electrostatic problems where you compute the potential and then you compute from that the electric field. So in most cases it's easier to compute this vector potential. So clearly the next step is, so you may wonder what this multiple expansions that we did for the electrostatics, how about here? Well, clearly we have a multiple expansion here too, and actually in a way it's simpler because already you know that the leading term of the multiple expansion is 0 because there is no magnetic monopole. So the next step here is what is the magnetic dipole. So before we do that, before I erase that, of course I need that one more time, but well, that is well. Before doing that, let's remember that I compute the energy of the electrostatic, the potential energy of an electrostatic field. Remember, it was some integral over the volume of the electric field square. Okay, so the potential energy density is the electric field square. What is the magnetostatic potential energy? This is important, because when we turn on the full Maxwell equations, then we are going to ask ourselves how the energy is organized in these fields. It's flowing from the fields to the particles, and there is conservation of the energy. So we are going to use this concept. So we know the electrostatic potential energy. So how about now the magnetic energy has to be a volume over some potential energy density that is the product of the current times the potential, vector potential. This is the, okay? But therefore we can rewrite this in terms of the, I want to rewrite this in terms of the B field, okay? To do that, I need Maxwell equations, because you see, J, right, this I can rewrite as, well, here, so let me put back the 1 over epsilon naught c squared. That comes out nicer here. So this term here is epsilon naught c squared divided by 2, the integral of, okay, J I can replace by the curl of B dot A integrated over a certain volume. and this is also B dot the curl of A by going around. But the curl of A is B, right? So you see the density of energy for static magnetic potential energy is again similar to what we got for is proportional to the square of the magnetic field. So at this point we can say that the total potential energy for static electric and magnetic fields is given by this density energy that is the square of the E field plus the square of the B field. Okay? So that's just by using this Maxwell equation and the definition of the potential energy. So that's just store it away somewhere. It will come back shortly when we start discussing the conservation of the energy for the electromagnetic field. And now we have time to go to this magnetic moment business. And that's, so what is the magnetic moment of some charges, some currents really? Well, again, we can just use we just solved the Poisson equation, right? So we just use the solution for what we need. So here again, I'm in this Gauss unit, and I write for this solution, right? And remember what we did for the multipole expansion. What you want is to expand this 1 over R. Then you look very far away from, so you have some currents here, right, in the volume V prime. And you look at this currents distribution at the distance R, and R is much larger than the typical size of this volume, R prime. So you want to expand the 1 over R minus R prime, exactly as we did before. So you remember that was a term 1 over R, the leading one. Then you had the term like this with the cube, and then quadruples and so on, but let's stop here. So if I do that and I include it in my integral, I get 1 over C, okay, I get this current J, maybe it's easier to do it. So let me write the component. This is a vector, so let me write the I component. So I put a I query. It's nicer this way. And then I put this expansion, right? 1 over R plus R dot I dot R cube plus whatever D3R prime. You see that this would be the this would be the monopole, but it's not there, right? And you see, this is the volume integral. Another way to see that it's not there is that, you see, if you take the continuity equation for the constant case, I mean, this is equal minus the change of charges. But clearly here the charges are all fixed. So you have the divergence of the J is equal to 0, and that's another way to see that this first monopole term vanishes. Of course it vanishes, the reason is because of this Maxwell equation, as we said. But another way to see that is there. So you are left with this term here. So let's the r cube term, so you can pull out the r cube. It does not depend on the r prime, and you are left with the integral of the I component of j in r prime, r dot r prime, d3 r prime. And then again, you have to use some gymnastic with these vectors. So let's see what I did. You take r dot r prime times j. Here you have j, right, these components. And this you can always write. So this is you see, you can, this time you go back to the you see, this looks like one of those terms of the triple vector product, right? Because the triple, so let me write it and then you recognize it. This is equal to r dot j times r prime minus the triple product, vector product of r cross j, right? So I'm writing the other way around. Usually we expand this in terms of this scalar product, but you can also do the other way around. And why is this useful? Because under integration, you see this one becomes minus 2 r dot r prime j, so that it can be taken on the other side to produce a common, let me write it, r 2c r cube cross the integral of r prime cross j r prime that you still have to integrate over the volume. So, so this one can be replaced by this one with a factor of 2 that goes here. And then you have this triple vector product. Now, if I define, so clearly if I define this to be, so this is what should be the magnetic moment, right? So I define the magnetic moment to this integral. You see, it looks like a, you know, the electric dipole moment was r times the charge, right? Here, clearly cannot be the same thing. It's really the vector product of the r times the density of current. So I call this m. Actually, usually 1 over 2c this is called m. Okay, so that finally this a is equal to this magnetic moment times r. That is this. You see, I flip those around, so the minus goes away. Divide by r cubed. Okay, is this clear or you're getting tired? What is not clear? So here I used again this trick of rewriting some vector. So this was this vector product. This looks like the same, so I get the factor of 2. So this is this triple product divided by 2. So this is the 2, this is the triple product. Then this looks nice because you see I can write it as r cross something. This something, I call it the magnetic. So this is the magnetic moment of this density of charges. So this is the leading term in this general solution of the vector potential for some distribution of elementary currents in this volume. And then what can we do? So why is this useful? Well, as much as the electric dipole moment was useful, because it's the leading term there. If you have an arbitrary distribution, then the most important term is going to be this. Then you have higher order terms like we had in electrostatics, but hopefully if the distance is large enough, those other terms are subleading, so you can roughly describe the situation in these terms. Actually, there are many applications of this magnetic moment in different situations. We'll see just one in a second. But first, maybe I'll give you another exercise for Monday. So we have the vector potential. So homework. So what is the B field? You have A. So if you take a curl, and if you are persistent, you get the magnetic field. So please verify that indeed the magnetic field looks very much like the electric field for 3n n. So if, okay, with R, if you put R cubed downstairs, it's like this, okay? So the magnetic field in R, due to this vector potential, so it's just a matter of taking the curl, so, but may require some work. So what is the magnetic moment for a little loop of current, right? This is the very simple current distribution. So take a little loop with surface area included, defined by the loop to be A. Okay, so M, this was the homework. This magnetic moment, well, I just used the definition, so it was 1 over 2c, right? The integral of r, so the magnetic moment here at the distance r from the center of some point of this loop, it doesn't matter because I'm really far away. We said that is r cross j r prime d3r prime. So if I have this little loop with the current I, again, it's like the density, I can rewrite it like 2c. Then I have the integral of r the integral over r prime I ds prime, right? Because this is d3, then this 3 becomes just the integral of that. So that I can pull it out, I over 2c, and I'm left with this integral r cross dr. But you see, what you remember what this, if you remember Kepler's law, that the area spanned by the areal element is just 1/2 r ds, right? If ds is this, the elemental area. So you see, you can write this integral just like is 1 over c, then 1/2 r dr is dA, So when you integrate, you get the entire area included in this circuit. And what is the direction of this? Well, it has to be because you see it's RdR, so it's RdR, so it's pointing outside, its norm to the little surface identified. So this is the magnetic moment of a little loop of current. Okay, so it's the elemental magnetic moment. So here you can do a homework, or maybe we do it together and then we stop as an example. Because you see, by following this line of reasoning, if you take a charged particle moving along some little loop, so take a charged particle with a given, so, well, let's do it this way. Take a charged particle moving in a central force field. So it's moving in a central force field at a certain distance r from the center of this force, okay? So it's like this, r dr. So again, you can use the area law, right? The total area spanned by this is some integral from one point to the other. And this, you remember, is the angular momentum dt. Or, in other words, if you integrate this is constant, right? Because it's a particle moving in a central force field. So I hope you still remember that the angular momentum is conserved. So this is just a constant, the angular momentum. So you can pull it out. And then you have to integrate over dt. But what is the integral over dt? This is the period of the motion in this central force, right? So the time it takes to the particle to come back. Think that it's moving on a circle or an elliptic motion, some closed motion in this central force field. Okay? Now you see that the magnetic moment, we just said that it was, I forgot the I is gone. The magnetic moment of a little loop, it was like this, but a charged particle moving in a closed orbit is like a little loop carrying what? A current, an electric current that is the charge divided by the period, right? The charge comes back, that's the electric current in that ideal loop provided by this charged particle in a central force field. So I can use this result for the magnetic moment to rewrite, so the magnetic moment of this charge moving in a central force, in a central field, is, I can use that formula, is I divided by C, right, times A. And what is the angular momentum is exactly, you see, you can write the norm of this as the, right, because the angular momentum of this particle comes this way, and the norm, the unit vector is just, I can write it as L divided by the size of that. So this is M. So I just rewrote that formula. Now, I use this result for the area, right? And the fact that the current is Q divided by the period. So let's collect everything. It's Q divided by CT, the period. Then I have this L divided by 2M, this term here. Then I have the period again, so it nicely simplified. Then I have this norm vector, like this. Okay, so this goes away, and this goes away. So you have Q divided by 2mc, Q divided by 2mc times the angular momentum. Okay? That's really nice. The magnetic moment of a charged particle moving in a central field is proportional to the angular momentum of the particle with a fixed coefficient that only depends on the ratio between the charge and the mass. In fact, ratio is very important because you see it's characteristic of the particles. So if you give me the particles, you give the mass and the charge of the particle, then they will move, they will just have all the same magnetic moment. If you So let's make a step further. Let's quantize the angular momentum for the L. Okay, so if we assume that L comes in some quanta of multiple of Planck's constant, then you see that the particle has the magnetic moment of this particle comes in multiple of a new constant that is QH. So here I get N H bar, so I get QH bar 2mc, right? And this you must know what's that? Bohr magneton. So, I mean, that's the rederivation, the way you derive Bohr magneton. That is the magnetic moment of a particle going around. For instance, I mean, this central force could be the force field generated by a proton, right? And then the electron going around will have that magnetic moment. That is some multiple of Bohr's magneton, QH bar divided by 2mc. Okay. Questions? If not, I think I stop here because now I finished what I wanted to say about magnetostatics. So next time we start with the full set of Maxwell equations and we move on from there.